we're very happy to be here. First, I would like to thank Lemaitre for the organization of the event, and especially Swan for the MC. Today I'm Valentin. I'm presenting with Raphaël a talk called Armor Type Safety with Iron. So we're going to talk about validation, types, and a lot of very funny things. So first, who are we? We are both backend engineers at Ledger. Ledger is a hardware company which is making secure hardware to secure digital assets, basically. So you're currently mostly of cryptocurrency and tokens. And Ledger are also a very large software part, which is a companion app and several backend systems. I'm team lead here, and I will let Raphaël present.
Hi, so I'm Raphaël, I'm senior staff engineer at Ledger. And I will tell you a story. You find in your code base a case class like this that just represents an event, with 5 parts on each string. So this looks good until you find something like this. And you try something, and yeah, it compiles. And it's a bug somewhere, you don't know where yet, but you know there will be something. So, how can we do better to avoid this kind of things? Say, okay, maybe we stack aliases. So, we define our 5 aliases and use them in the case class, but that's the same thing, except it's more readable. And only the 2 problems we saw still exist. So maybe with value classes, we define them and we test them. So here, let's look good. This does not compile anymore, but this compiles and still doesn't work. So we say, okay, we validate values. First, we use the good old require. It works. If that's an invalid value, it will crash, but we will know as soon as it arrives. But yeah, we don't want to crash the app because someone inputted a bad value. So we validate in another way. So first we define our error class, which is just an exception for my error, and then in our value classes, in the companion object, we define a parse method that returns a neighbor to know what is the error, and or return the good one. And after, we implement it, saying the condition and what is the message that will be given if the error occurs. And we have to do this for our 6 classes. Sorry. So let me the implementation. After, we don't want to do to have the value class really exposed. So where it's class 3, so let's use object types to hide the value of this. So we define our here we define the object type extending a string in order to be able to to use string methods on it, and define one extension on the opaque type to get the real value. It's the unwrap method, and another one to wrap a string to make the opaque type. And also we have the pass method to write because we have to at the time. So we saw some method. First row classes, we don't have what we want to be legible, although have validation to be able to be used in a pure way with referential transparency. We don't have performance because everything's runtime. And if I go back here, I didn't write how we use it, but as we have the bars we need for comprehension, making the six instances of the opaque types or the value classes, and then you can have your eval. So we have to find something smarter, with less boilerplate and more performant.
Okay, so I will also tell you a story, actually. Before discovering this fantastic library called Iron, we made our own abstraction over opaque types and to streamline validation and so on. And this added a lot of complexity actually of the code base, because if you go behind here, the validation here doesn't compose. It doesn't compose well. You have to reduce validation or the composition of either each time you want to have something. So if you have one constraint, you have to have one value type, then another constraint, you have to grab this value type into another one and so on. So we are very delighted when we found this. So first, what is Iron? What is Iron is a composable type constraint library, and we'll get back to all the terms. It's created in Scala 3, so we only use Scala 3 at Ledger, I forgot to mention it before, by Raphaël, which is here with us today. We have, and it make us able to embed constraints to specific types and to share constraints between types. So let's focus on this library. First, what's a constraint? We'll get back to the basics, and actually we'll show you how it is implemented from scratch in Iron. To have a constraint of the type, we have to implement a given instance here, which take a dummy class, just a final class. Actually, there is no instance of this class at all. Actually, it's just a dummy symbol for the compiler to be able to do positive, for instance. And then we can implement a constraint trait, which could be also written int constraints positive, actually, to have an inline f, which is test function, actually, a predicate, and a message. And actually, this uses the capacity we had in Scala 3 to have forced inline number strings, which is a very powerful feature to force your user of your library to be efficient, actually. So we say it's a type constraints. So how do we apply constraints to type? It's very simple. We use this very funny operator here, which is an aliases for another structure that I won't get into it today, which means the int is constraints to be positive. And actually, this is validated at compile time. This will compile if and only if the one is a positive integer. And actually, if we put -1 and we compile this, it will fail with a very nice error. That we don't have example of error, but it's very nice error described to tell you that we will put it a wrong value at compile time. Then the good thing with this is that it's composed. Actually, you can describe two constraints and use Boolean logic to combine them. So you have not, you have and, you have or, and you can combine all of these to get nice and factorized constraints of your types. And actually, if I unfold this, -1 still doesn't compile, but also 1 to 3 won't compile either, because actually it's between 0 and it must be between 0 and 4. So next, the interesting thing is not only the compile time features, but we've seen we can use it to do runtime validation also. So first, in fact, you need to know the value at compile time to be able to apply constraints using like this, using the equal behavior. So this won't work at all. Actually, it will tell you it doesn't know how to expand the value at compile time, so it will fail. But if you do an inline val, for instance, it will, because actually an inline val has no existence, it will just be inline by the compiler, so this works. But if we really want to use a runtime value, for instance, in your HTTP inputs and so on, we can use refine. And actually, this example method is defined in all constraints types and allow you to get a value which will actually crash at the runtime. It's the equivalent of require, actually. But the good thing with this is like if you define the right constraints, you also have methods to do refine either or refine option. For instance, here we do the same constructs. Imagine we do the same constructs to construct an IBAN, but here we refine either with the constraints here. Actually, this is very awful because I should have factorized the constraints away. But to get you a feel of what it is to program with Iron, actually, you have more certitudes about your typing because you embed the constraints into the type system. And here we do a for comparison. And we refine all the things to have something which is alphanumeric. Actually, we should have also, we could have a stronger constraints. The IBAN have stronger constraints. I think the set of letters is fixed and so on. So we could have a regex to compile, to check in the type system that it is a good value. And then the constraints also the length, because it was a big issue we have using IBAN.
Sorry, why do we ignore all the other variables? It's just function.
Oh, where?
Okay,
because it's totally copy-paste. don't look at it. It doesn't exist. Because we have even better, because having constraint type is good, and the best part of it is like there are subtypes of real types, so you still get all the methods actually. But the thing is, if you have two integers which are refined positive. For instance, if you have a double ledger contability and you have spending and expenses, then the two constraints will be the same actually, because that needs to be eligible money, so it's strictly positive. But if you want to constrain what is the nature of your type, with the validation, you can do opaque types. And actually, Iron has a very nice helpers for combining opaque types with constraints. So here I define a positive type, which is a subtype of integer, which is an integer which is equal to 0 actually. And then I can use the refined type of magic here. It's not magic, it's just extension method actually, to be able to implement all the convenience methods. So you get either a constructor, option constructor, the unsafe constructor, the compile time value constructor. You get a lot of goodies actually from this. For instance, this is a real example from our code base. So at Ledger we manipulate a lot of cryptocurrency. So it is sats. Sats is an atomic unit of Bitcoin. So Bitcoin is 10 at the power 8 sats. And so we can constrain it very much because we know it's only positive amounts, and the total value of Bitcoins actually is capped. So we can constrain it to be always a legible value of Satoshis. So we, when there is a constraint which is a bit long to write, we usually put it into private type, and we reuse it to not having to redo the same syntax tricks. Actually, this could be much more readable once the Scala-free compiler engineers will have the erased keyword, which is sadly missing. But once it is normally, once it is erased and very understood we could have a much better user experience. But it still works for us. Okay, so we let Raphaël.
Yeah. So one thing about Iron that brought us a lot, it's at feedback loop for validation, because in the end, everything is how much time do we need to find a bug. So, worst case scenario in production. It's a long time, so it's really expensive. If we have a chance, we see it in staging. Or better, we try to have a good test coverage, but in integration tests. But it's always at the time writing tests, running them, and with integration test it can be really long. Or unit tests, but the better is a really good compilation time, and that's where Iron gives us really good satisfaction. And so if we go back to the previous table, we see for all these techniques, Iron check all what we all constraints that we want. So it's really readable. There's no possibility of substitution in calls, in function calls or constructor calls. It validates.
Integration. It's a bit the true successor of Refined. I think a lot of you have used Refined using Scala 3, Scala 2 domain model validation. And Iron allows us to do more because it composes much better, and actually it has a true runtime cost, true zero runtime cost. So it's ecosystem. Actually, you have extension methods with cats and ZIO validation, so you can do parallel collecting of all the errors actually. It adds methods on both opaque type arrays aliases, so refine type ops with solution, and on types just to refine validating or refine validation and so on. So this is good to have good user input. And when we are good for input, because it's also used in a lot of libraries which make a typical Scala microservice or service tech stack. Actually, it's integrated very well in Tapier. So you can have a codec for Iron types quite natively. You also have all the JSON support you need, either it is CRC or JSON if you need more performance, or JSON. You can use it with Doobie and Skunk actually. Doobie, it's merged, but not published yet, but at least it is in the repository actually. You can do configuration with Cyrus, which is a very nice library to use configuration. Actually, with the type level stack, if you have not checked it, it's very good. And then you can have an arbitrary instance using the Scala check, so you can either generate instances of your other types. This is a real example actually from OpenBase. This is a tag class we have to tag accounts in our system. It has a tag name, tag value. The both are constraints in database and constraints with Iron. And actually, the validation we have on this tag, you will see it is a head from the Tapier description to the databases and back and forth. So here you have two. The string must not be empty and have a max length of some limit. With the Tapier integration, you can just query an option of type if you need to have it run in your services. And that's it. Basically, it parses and validates the inputs. It is using the native Tapier validator framework to do it. It compiles the validator from the topology of the type, if and or and so on. It will be followed by the Tapier implementation. We also use it with Doobie, so you can see we also do very nice SQL. So both output ID and tag name tag value are opaque types actually, and they are just interpolated natively here. It doesn't highlight. It's a little but if the wire close, it normally you can see that with account name value which are interpolated, so it is translated into reverse statement filling at some condition. And then integrating with iron is easy because you can see here actually is the entire integration of iron with the type class of 2. And that is, there is no more code necessary. And yet there is a nasty as instance of, because actually when you are using global types, think about it, they are just equal in terms of types, so you can just do as instance of, so you can see that there is much less cost to integrate with iron than with something like refine. It's also using the refine typeops mirror to use the refine typeops integration. Refine typeops is ideally the thing we extended is the object companion of the opaque types, if you get back to it. And this allows us to get the constraint types, the iron type, from the mirror. So we have a very nice example of dependent types in Scala 3, which is very good. And yeah, so what are the takeaway from this presentation? Mainly, we love iron because it is making illegal states unrepresentable. Actually, it's a quote from Jan Minsky, which is a lead engineer at Jane Street, which is mostly working with OKM. It's the same functional coding issue, actually. And this is very the key to have a stable and reliable system is to be sure that there is no input which is validated to it. And iron it's very easy to have inputs validated. Then think about it, the only dependency of iron is Scala 3 compiler. So the site system is very huge in Scala 3. It is very well done and props to the Scala compiler team because they have done an awesome job doing inlines and all this compile time operation which allow us to have this strong and light at the same time library. And then it really increased the reliability of our code that we have certitude and like being sure something is processed in programming. It might happen, but yes. Being sure of things is precious. If you know that as your type system you have some, not an int, but something which is more than an int, it will allow us to have a better system. So thank you for your attention. I hope you have a great time. We are going to get the slides actually because it's hosted on Raphaël